Okay, Assalamualaikum. Good day to all. So now we will go with chapter 2, which is matrices. So this is part 1, which is consists of introduction, type of matrices, operations, determinant, and inverse. So for today's video, I'll just cover up to operations only. So what is a matrix actually? So matrix is a rectangular array of elements or entries Aij involving m rows and n columns. Okay, if we have A, here example A is a matrix. So here is what we call row. Okay, the horizontal one is row. Row 1, row 2, row 3 up to row M. Okay, this one is what we call column. Okay, the vertical one, column 1, column 2, column 3. So to write the order of the matrix is we write m times n. Okay, the number of row times the number of column. Okay, so am by n, the order is m by n, meaning m is the row, number of row, and n is the number of column. Okay, so that is a very basic thing of matrix. Okay, actually this is the definition of 2.2 from the textbook. So two matrices A, Ij, element m and m times n, and B, element bi equals to Bij, element mrs. Okay, here meanings matrix A. So the element, okay, the element or the element, the element and entries or entries of A, we write it Aij, A11, A12 up to Mn. M is the number of row, N is the number of column. So the same thing for B, the element is B, B11, B12 up to BRS. So they are said to be equal if M, the number of row of the A, is equals to the number of row of B, matrix B, and the number of column of matrix A is equals to the number of column of matrix B. Then only we can say that A is equals to B. So if Aij or a particular element I is equals to J, then the entries A11, A22, A23, okay, and so on are called the diagonal of a matrix A. So find the values for the variables so that the matrices in each exercise are equal. Okay, for example, this one. So you can see here this is matrix A, this is matrix B. So both have order 2. It's 2 by 2. 2 by 2. So x plus 1 must be equals to 10 since they are equal. And 2z must be equals to negative 6. Y minus 2 must be equals to negative 4. Then only we can say that they are equals. Okay, x plus 1 is equals to 10. Y minus 2 is equals to negative 5. And 2z is equals to negative 6. So we can solve it. X is equals to 9. Y is equals to, what do we call it, negative 3. And z is equals to negative 3. So that's it, how you solve it. So this is just want to explain what is equal to equalities of two matrices, and also the diagonal. Diagonal is this one. Okay, this is one we call diagonal. Okay, because of a matrix, okay, A, we have A11, A12, A21, A22. Okay, remember we write the number of row first. This is row 1, row 2. This is column 1, column 2. Okay, row 1, row 2, column 1, column 2. So where is the element of A11? So it's here. A22 is here. This is what we call diagonal. Okay, this is diagonal. The same thing for element B. Okay, so these are some type of matrices that you need to know. First one is square matrix. What is square matrix? Square matrix is where the number of row is equals to the number of column. So you have a matrix A with order m by n, where m is equals to n. So it's a, maybe we have A22, so A11, A12, A21, A22. This is 2 by 2. You have A33, it will be A11, A12, A13, A21, A22, A23, A31, A32, A33. This is example of square matrix where m is equals to n. Okay, m is number of row, n is number of column. Diagonal matrix is where you have like this. Only element on the Aij where I is equals to j have values. If it's 2 by 2 like this. A11, A22. Everywhere else will be 0. Okay, diagonal matrix. This will be a square matrix. It's a square matrix, but only the diagonal have value. A11, A12, A22, A33. So A12, A13, A21, A23, A31, A32. See, like this. So this one will be 0. Except the element on the diagonal only we have value other than 0. It's not 0. It's not 0. Okay, so this is called diagonal matrix. Okay, see, you have the value here. What about a scalar matrix? So a scalar matrix is actually a diagonal matrix. Okay, but we have a uniform value of the diagonal. So the diagonal should be k, k, and k. It's a diagonal matrix, okay, but the value of the diagonal is the same, whether it's just 3, 3, 3, 2, okay, 3, 3, 3, 3, 2, 2, 2, 1, 1, 1, negative 1, negative 1, negative 1, but not 0, okay? So this is called scalar matrix, a diagonal matrix, but the diagonal is uniform or same values at the diagonal. Identity matrix is actually a scalar matrix, but k is equals to 1. So we have 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, if it's 2 by 2, 1, 0, 0, 1. This is called identity matrix, where k a scalar matrix, okay, but it is 1. The entries for the diagonal is 1. How about zero matrix? Zero matrix meaning the entries are zeros. For example, okay, upper triangular. Okay, Upper triangular, all of these are square matrix. Upper triangular, you have the diagonal A11, A12, A13. For example, the 3 by 3 matrix. So upper triangular, meaning the values here are zeros, but here is not. 1 3 A, so this is 2 2 A 2 3. So you can see it's like a triangle. Triangular here. It's like a triangle where it's upper above the diagonal. So we call it upper triangular. If it is a second order, A11, A22. So A12, A13. Sorry. A22, A12. So here will be 0. Okay, if it's lower triangular, can you guess it? Okay, it will be like this. A11, A22, A33. So here will be 0. Okay, because it's lower triangular. The triangular is lower below the diagonal. You can see here, it's like a triangle here. So it's lower triangular. So if it's you want to write in for the 2 by 2, A11, A22. So it's 0 here. It's A21 here. Okay, you see, you can also see a triangle here. So that's it. Very quick for type of matrices that you need to know: square matrix, diagonal matrix, scalar matrix, identity matrix, zero matrix, upper triangular matrix, and also lower triangular matrix. So what is a negative matrix? So a negative matrix of A of order n by n is noted by negative A, where we put the negative to each value of the matrices. For example, you have A, A is equals to 1, negative 1, 2, 0, 4, 3, negative 7, 1, 2. Okay, so the negative of A is where you put negative to each element or entries in the matrix. So it's become, you multiply by negative 1, negative 1, 1, negative 2, 0, negative 4, negative 3, 7, negative 1, negative 2. So that's it, what we call a negative of a matrix. Next is matrix transpose. Matrix transpose, if you have A of order n by n, okay, meaning row is m and column is n, then the transpose of A, okay, transpose, we write it as A transpose. So meaning we need to transpose every element. So meaning they change, the A becomes n by n. For example, we have A is equals to 7, negative 2, 4, 5, 0, 1, 6, 10, negative 1. Okay, we have like this. So if we want to find A transpose, okay, meaning the first row here becomes the first column of the A transpose. So it will be 7, negative 2, 4. Okay. You see here. And then 5, sorry, the color change. Okay, 5, 0, 1. The second row becomes the second column, and third row become the third column. That's how you do it. Okay, it's just the difference is one. Okay, we transpose, meaning we change the row becomes column, column becomes row. Okay, I hope it's clear. This is what we call a transpose. Okay, we transpose of a matrix, matrix transpose. So what is symmetric matrix? So a square matrix n by n, okay, is called a symmetric matrix if AT is equals to A, where the elements obey the rule Aij equals to Aji. So meaning after you have performed the transpose operation, matrix transpose, you still get the same matrix. Okay, maybe we can look here. Okay, A transpose is equals to what? 1, 2, 2, 4, right? It's the same thing that you will have, that you will get. So AT is equals to A. So this is symmetric. Do you have any idea of another types of how we call it symmetric matrix? So I give you another one. B. Okay. First we write the diagonal -1, 2, 3. Okay, 3 by 3 matrix. So A11, you let it equals to 4, for example. So A21 must be equals to 4 too. Okay, like this. Then only you can say it's symmetric. And then A13, let's say we put it 5. So A31 must also be equals to 5. Okay, and then here A23 is equals to 7, for example. So A32 must also be equals to 7. Okay, let us check the B transpose. Okay, first this column. So we obtain -1, 4, 5, and then 4, 2, 7, 5, 7, 3. So we perform the transpose. Is it still? Now we look at the whole thing. The whole thing here. Is it the same? -1, -1. 4, 4, 5, 5, 4, 4, 2, 2, 7, 7, 5, 5, 7, 7, 3, 3. So it's still the same matrix. So again, this is B transpose is equals to B. So this is the matrix B is also symmetric. Okay, as simple as that. So next we also have skew-symmetric. What is skew-symmetric? So it's still a symmetric or a square matrix. Okay, it's skew if A transpose is equals to the negative of A. Okay, so where the elements obey the rule Aij is equals to the negative of Ji. So the leading diagonal must contain zeros. So that the leading diagonal must contain zeros. So a typical skew-symmetric matrix over the 3 by 3 is given as this one. Okay, for example, if you want to transpose this row, so let us let this matrix equals to A. So A transpose is equals to 0, 1, 3. Okay, next is -1, 0, -6, and -3, 6, 0. Okay, same thing here. Sorry, here. And then we have this row becomes this column, and this row becomes this column. So we perform the transpose, right? So if we can see the overall, okay, overall 0, 0, 1 become -1, 3 becomes -3, -1 become 1, 0 becomes 0, -6 becomes 6, -3 becomes 3, 6 becomes -6, 0 becomes 0. So as we can see, that it's the negative of the matrix, right? If you want to write it clearly, it's actually negative 0, 1, 3, -1, 0, -6, -3, 6, 0, which is exactly the same as this one, right? 0, 0, 1, 3, -1, 0, -6, -3, 6, 0. Exactly the same thing. So this is actually equals to A, negative A, sorry. When AT is equals to the negative A, this is what we call skew-symmetric matrix. Okay? So next is row echelon form. Okay. An n by n matrix A is said to be in a row echelon form REF if it is satisfying the following properties. The first one, any rows consisting entirely of zeros occur at the bottom of the matrix. Okay. For each row that does not consist entirely of zeros, the first non-zero entry is 1, called a leading one. So for each non-zero row, the number 1 appears to the right of the leading one of the previous row. So first, okay, we look at the example. Okay, for number 1, any row consisting entirely of 0 occurs at the bottom. Meaning, if you have row which has 0, 0, 0, so it must be at the bottom. You cannot be here or here. Must appear at the bottom of the matrix. Number 2, for each row that does not consist entirely of zeros, the first non-zero entries, okay, meaning, okay, the 0, 0, 0 is below here at the bottom. If there are rows there is not 0, for example, we have 1, 0, 0. The first thing you want to see from the right, okay, from the left, when you look here to each column or to each row, for example this row, you'll see number 1 first, right? From the left, you ignore the 0, you must see 1. It cannot be 2. When you look from the left, the first non-zero entry of that row, you must see 1. So this is what we call leading one. Okay, leading one. For each non-zero row, the number 1 appears to the right of the leading one of the previous row. Okay, it's been like this. you have 0, 0, 0, right? And then you have leading 1 here, 1, 0, 1, and then 0, 1, 0. So the leading 1 is here. This is the leading 1. Leading 1. So leading 1. Kita nampak pula. Leading 1. Leading 1 of leading this is leading 1 of row 1, leading 1 of row 2. So this one all zeros, so there is no leading 1. So the leading 1 cannot be here. The number 1 cannot be here because it have to appear to the right, okay, to the right of the first non-lead of the leading 1 appear before the row. Okay, we look at the example. For the following matrices, determine the matrices whether the matrices is REF or not. If the matrices are not REF, give reason. Okay, A is equals to 1, 0, 0, 0, 0, 0, 0, 0, 1, right? So is this REF? No, right? Because we have this one. This one should appear at the bottom because it is all 0 rows. 0, 0, 0, it must have at the bottom here. It must be at the bottom. Okay, must be here. Okay, and then B. Is there any all zeros? Okay, a row consisting of all zeros. No, right? So we skip it. If there are any, it must appear at the bottom. If there's no all 0 rows, we can omit the properties. The first property. Okay, and then we look at the first one, leading 1. So we look row by row. The second one, we look from the left of the row. You can see what we see first. We see a leading 1, number 1. And then move to the second row. Okay, you see 1 first. And it's also appear to the right of this one. Right? Here is the first leading row, leading 1. Okay, and then we look at the third row. You see 0, okay, 0. Okay, so you see 1. So this is REF. So it's appear to the right. The leading 1 appear to the right of the previous leading 1. Okay, of the previous row. So this is REF. This is not REF. Okay, that's it. This is very important later when you want to find inverse and also solve for the matrices. So this is one more form, which is reduced row echelon form, or we say RREF. Okay, sorry, RREF. So it's the same thing. You have all 0 entries row will be at the bottom, and then for each row that does not contain and consists of entirely of 0, the first non-zero entry is 1, called leading 1, and for each non-zero row, the number 1 appears to the right of the leading 1 of the previous row, correct? And then we have, if a column contains a leading 1, then all other entries in the column are 0. Okay, this one is correct. So for the meaning, you look at the column. Okay, if the column contain leading 1, then the other entries of the column must be 0. So we look at the example to be more clear on this. Okay, determine whether it's RREF or not. Okay, RREF, reduced row echelon form. So A, is there any row which contains all zeros? Yes, here, right? So it's appear at the bottom. So correct. And then we look row by row. Okay, row 1. Okay, we see number 1 first. So this is the leading one. And then row 2. We see number 1 first. Row 3. Yes, we see number 1. So condition number 2 satisfies. And then condition number 3, we can see that the leading one of the next row appear to the right of the previous row, right? So okay. How about the last condition? If a column contains leading one, then all other entries in the column are 0. So now we look at the column. So column 1. Here is column 1. Yeah, 1, the others are 0, right? So, okay. And then column 2, which contains leading 1. Yeah, it's all 0 elsewhere. And column 3. Yeah, it's also 0 elsewhere. How about this one? It's okay. We don't have to check this. Okay, we don't have to check this column because it does not contain any leading one. So we just need to focus on the leading one. So this is RREF because it satisfies all the conditions. So how about condition B? Yeah? So we have the all zero rows. Sorry, the row contain all zeros at the bottom. So we look at the leading one. Okay, row by row. So row 1, yeah, we see number 1 first. Row 2, we see number 1 first. So it's appear to the left, sorry, to the right of the previous row. Okay, this is the leading one. Correct. So now we check for condition number 4. Okay, so this row, there's no leading one. So no need to check. So this is contain leading one. Okay, zeros elsewhere, the same thing is zeros elsewhere. Okay, so we don't have to check this column and this column because there is no leading one here. So all conditions are satisfied. So this is also RREF. Okay, I hope all of you know how to determine REF and RREF. So just follow the condition here. 1, 2, 3, 4. So now let us learn on how to add two matrices. So before you add matrices, you need to know the condition for it to be valid. Okay. So if A and B are matrices of order m by n, so matrices C, which is A plus B, is defined by C. Okay, meaning we add together the element of the same location. So two matrices and A and B will be said conformable for addition if and only if they are of the same, only if they are both of the same order. Same order meaning 2 plus 2, 2 by 2, 3 by 3, 2 by 1 equals to 2 by 2. It's the same order. Okay, let's check for A plus B here. A plus B is equals to negative 1, 2, 0, 1 plus 1, 3, negative 1, 2. So it will be negative 1 plus 1, 2 plus 3, 0 minus 1 or plus negative 1, 1 plus 2. So we obtain the answer is 0, 5, negative 1, 3. So that is A plus B. Because this is 2 by 2, this is 2 by 2. So we can perform the operation. How about number 2? This is 2 by 3, number of row times column. This is 2 by 2. So it's not the same. Okay, so cannot be obtained because it's not conformable for addition. Okay, because the number of order is not the same. So if it's 2 by 3, it must also be 2 by 3. Okay, so to add it is very simple. You just add element of the same location. Okay, 1 1 add with 1 1, 1 2 2 with 3, 0 with 2. Okay, this. Okay, so next is subtraction of matrices. Is basically the same concept as addition just now, but the operation now is minus. So two matrices A and B will be said conformable for subtraction only if they are both of the same order. The same thing, it must be of the same order, then only you can minus. Okay, let us look at the example. It's given A, B, C. So what is the order of A? A is 2 by 3. B, 2 by 3. How about C? 2 by 2. So what is B minus A? B minus A is equals to 3 minus 2, 1 minus 6. Oh, sorry. 2 minus 3, 6 minus 1. Right? 1 minus 1. 10 minus 0, negative 3 minus negative 2. And 6 minus 4. Okay, so we have it negative 1, negative 5, 0, 10. This one is negative 3 minus 2. Right? Okay. Negative 1 and 2. That's it. Okay, where we perform the operation. Like this. So here, this one here, and so on. Okay, 2 minus 3, 6 minus 1, 1 minus 1, 10 minus 0, negative 3 minus negative 2, and 6 minus 4. So we obtain this answer here. How about B minus C? B and C. The same thing we cannot obtain. Cannot be obtained. Why? Because it's of this different order. It is 2 by 2, this is 2 by 3. So we cannot solve it. Okay, so be careful. So next is the properties. So if addition, this is just for your knowledge, okay? A plus B is equals to B plus A. Okay, and then B plus C is the same as you add B and C first, or you add A plus B first. So if A add by a 0 matrix, you will get A. A plus the negative of A will get 0. So next is the scalar multiplication. Very simple. When we have a scalar, a number, okay, a number, a real number. So the scalar multiplication is denoted as alpha. if we have alpha as the scalar alpha element real number, okay, then the scalar multiplication is denoted as alpha a, okay, where we multiply alpha to each element of a. Okay, for example, if you want to calculate here in this question example, a is given as this one, you want to find negative 2a, so negative 2a is just you put negative, or we multiply negative to each element or each entries of the matrix. So negative 2 times 3 is negative 6, negative 2 times negative 1 is 2, negative 2 times 0 is 0, next is 4, negative 2, negative 6, 0, 2, and 4. So we obtain this answer. Okay, the same thing if you want to find negative a, so you just multiply by negative 1. Okay, remember for scalar multiplication, we just multiply to each entries of the matrix. Okay, that's it. Scalar multiplication. So here are some properties of scalar matrix. Okay, and this is just for your knowledge. Okay, next is matrix multiplication. So please pay attention on this because this is quite important, okay, for you to know. Because if you miss this concept, so you will miss a lot of things. So suppose A is an m by n matrix, okay, A m by n, and matrix B is a PQ matrix, meaning the order of A is m by n, the order of B is P times Q. So for the product of AB to exist, it must be that n is equals to P. Okay, meaning the number of column of the first matrix must be equals to the number of row of the second matrix, must be equal. So, example 2.18. First, we write the order. What is the order here? It's 3 by 2. And this one? 2 by 3. How about this one? 2 by 2. 2 by 2. Find each product is, if it's defined, okay? AB. Okay. AB, you see, the number of row of column of the first one is equal, is same. Second, the number of column of the first matrix is equals to the number of column of the number of row of the first number of row of the second matrix. Same here. So 2 2, so we can perform the product. Okay, the result will be equals to 3 by 3 matrix. Okay, I write it again. If it between 3 by 2 with 2 by 3, so here AB must be the same, and the result that we will obtain is 3 by 3. So the resulting matrix should be 3 by 3 of order 3 by 3. If not, you are doing it wrongly. Okay, so A times B is equals to 4, 2, 6, 1, 3, 5 multiplied by 2, 3, 4 -1, -2, 0. Okay, so we should multiply this row, this column. Okay, first thing we need to solve for row to each here. Okay, so what do we get? This is for the first row. 4 times 2 is 8. Plus 2 times -1 is -2. And then we obtain the second element. 4 times 3 is 12. 2 times -2 is -4. And then the third element, this one. 4 times 4 is 16. 2 times 0 is 0, so the answer is 16. Okay, settle for the first row. For the second column, it will be bottom row. This row with this one first. So it will be 6 times 2 is 12. 1 minus times -1 is -1. And then 6 times 3 is 18. 18 minus 2. And then the last column should be what we call it, 24 minus 0, which is 0. Okay, we should also do for the last column or last row, which this one first. Okay, so we obtain 6 minus 10, and then 9 minus 10, and 12 minus 0. Okay, that's it. So you can simplify it. So we continue here. 6, 8, 16, 11, 16, 24, -4, -1, 12. So this is the answer for A times B. How about B times A? So if it is B times A, okay, B times A, so we look at the what we call it, the order. B is 2 by 3. How about A? 3 by 2. Okay. So we can perform the operation because it's the same, and the resulting matrices will be 2 by 2. Okay, 2 by 2. So BA is equals to 2, 3, 4, -1, -2, 0, multiply by 4, 2, 4, 6, 3, 2, 1, 5. Okay, so I'll continue. So I just erase this one, okay, because I finished that one. So BA, okay, continue here. So it will be 2 by 2 matrix. So we solve row by row. So row 1, this one. Okay. So it will be 2 times 4 is 8. 3 times 6 is 18. 4 times 3 is 12. Okay. And then the second one will be 4 times 6. 2 times 2 is 4 plus 3 plus 20. Okay. And then for the second one, second row, okay. So negative 1 times 4 is negative 4. Negative 2 times 1 is negative 2 times 6, negative 12, and 0 is 0. Next is for the second column, negative 1 times 2 is negative 2, negative 2 times 1 is negative 2, and then we have 0 there. So the answer is actually 36, and then 27, negative 16, and negative 4. That's it. How about A times B times C? So B is 2 by 3, C is 2 by 2. So you see here, it's not the same. It's not the same. 3 is not equal to 2 here. So B times 2, B times C cannot be obtained. So you must remember the critical part of the matrix multiplication is n must be equals to P. The number of column of the first matrix, okay, A, must be the same as the number of row in B, the second matrix. So these are some properties of matrix multiplication. So that's it for matrix operation. So you have to do the exercise provided in the Google Classroom. Okay, thank you very much.